Well, welcome to question 3 from Chapter 4 of Fundamentals of Particle Technology. It's a cake filtration question again, just like the previous one, and it does follow on from the previous question. The previous question was at constant pressure, though this is going to be at constant rate. The box out is a good place to start here for the solution. The equation for constant rate filtration is actually given here. It's a very straightforward form of just adding the pressures together between the pressure drops due to the cake, that's this term here, and the pressure drop due to the filter medium. And we maintain a constant rate, which is what dV dt is just here. So that's constant rate. That is the cumulative volume of filtrate, and that is the total pressure, the pressure drop over both the filter medium and the filter cake. So what does that look like then in terms of a plot? Okay, well, in terms of the equation, what we're expecting to see is delta P increasing as a function of volume from some intercept, and that should be a straight line. Okay, so this equation here is effectively a y equals, this equation here is effectively a y equals mx plus c type equation. By definition, we have the constant rate, so that's a constant. If it's an incompressible cake, then everything else inside here is a constant. So our independent variable is the volume of filtrate. And then the intercept is this collection of terms here, because again, by definition, we're at constant rate, dV dt is a constant, and everything else, the viscosity, the filter medium resistance, and the filter area is a constant. So we should have this straight line on a pressure against volume. And it would actually be a straight line if you were to plot pressure drop against time as well, because there's the proportionality between volume filtrate and time. I think it's probably worth just noting that down actually. So, you know, we are dependent upon observing something looking like this for filtrate. Okay, there's nothing to start with, there is no intercept here. Volume of filtrate is 0 at time equals 0, and it obviously goes up like that. Now the reason why I wanted to draw that was to emphasize the point that dV dt, the rate of change of filtrate with respect to time, is going to be equal to capital V, the cumulative volume filtrate, over cumulative time. Okay, and we're going to need this expression later on, so that's an important expression, and hopefully you're with me that it makes sense courtesy of the graph that I've just drawn. V against T is a constant, hence you have this straight line that goes on for however long we want to filter, and it's also true that the differential will be equal to the same gradient. Okay, so that's an important relation. Okay, well, I just want to take a little tangential sort of area, a tangential sort of viewpoint here. Why might we be interested in constant rate filtration? It is greatly underrated. Constant rate filtration is actually a very useful way to run a filtration. Very often, actually, it's the first stage of a constant pressure filtration. I mean, if we have a pump, let's say a progressing cavity pump, so I'll just call that a progressing cavity pump, I'll just call it PC. So we have a feed coming into the pump, we have the discharge from the pump, it's not a centrifugal, it's a progressing cavity, and we were to feed a filter press, for example. So a filter press, we just have lots of plates and frames inside the filter press, and the filtrate discharges underneath, but the solids stay inside the frames. Okay, so a plate and frame filter press, we would anticipate the performance of a progressing cavity pump to be something like this. So if we were plotting the pressure, which is the inlet pressure into the filter against time, we would expect to look something fairly similar to the graph that we've just been talking about, the delta P against V curve, and then we'd expect it to bend over and just carry on at a constant pressure. So this is typically how a filter press would operate, where we have to start with the constant rate, so I'll put a bar down there, Q, and then we have a constant pressure region just here, where some form of safety valve or possibly bypassing inside the progressing cavity pump has even taken place. So we're now effectively running at a constant pressure all the time. So it's very common to have constant rate then followed by constant pressure, and that could be something in the order of 4 to 6 bar. They're fairly common maximum pressures that people operate these sorts of devices, the filter presses, at. You can get higher pressures as well, but these are the sorts of filter presses that have been around for 100 years or so. So it's an important equation just here which we'll be using to do the solution, and there's the important concept that dV dt equals V over T. So if we actually move into solving the problem, and I think what I'll do here is I'll just make the problem a little bit more readable. Maybe another one. Yeah. Okay. That's good. So what have we got? Well, in the problem we're given an equation, an empirical equation, and the empirical equation is probably best looked at, thought about, and then interpreted into an algebraic equation which says that delta P equals 168 T, okay, where T is in seconds, plus a constant of 6670. So that is our intercept on the pressure graph. That's our y equals mx plus c equation. So we have the standard linear equation, y equals mx plus c, and that's what we're saying will be our pressure curve, our pressure it's not a curve, our pressure graph. So that's delta P plotted against V in this case, so I'm using V for the independent variable. Okay, well, what was the filtration equation? The filtration equation was delta P, total pressure drop, is equal to mu, which is the viscosity of the filtrate, the specific resistance of the filter cake, alpha, little c, the dry cake mass per unit volume of filtrate of the filter cake, the filter area squared. I'm going to put dV dt here because that puts all the constants together, because by definition we're operating under constant rate, so dV dt is a constant. V and T aren't a constant, but dV dt is. And then there we have our volume, the independent variable, the cumulative volume of filtrate at any one time. And then we have the pressure drop over the filter medium, which is the viscosity of the filtrate multiplied by the filter medium resistance, or filter cake resistance, filter cloth resistance, sorry, and then that's all over area. And again we have dV dt just here, but that's a constant. You know, dV dt is a constant, hence we have that intercept. So that's what our equation is, and the initial questions are really just answered by looking at that equation and a little bit of thought. We're going to use the values from the previous question, the values for specific resistance, dry cake mass, filter area and viscosity. So we're going to have to refer to those. But the pressure drop over the filter medium doesn't need any of those. The pressure drop over the filter medium is clearly tied up in what we have here. If you compare these two equations, the empirical equation and what we know to be a constant from our filtration equation, clearly the pressure drop over the filter medium is 6670. So the answer in part 1, what's the pressure drop over the filter medium during the filtration? 6670. Okay, that's nice and straightforward. Now the next part though, it does require us to make a calculation. We're interested in the constant rate and in order to solve that constant rate we do need these two bits just here. Okay, and these two bits are to do with the pressure drop over the filter cake. Empirically, the pressure drop over the filter cake is equal to 168 times T. I guess really I ought to have gone over, I ought to have said that was the same as what's over here. Sorry about that. So 168 times T is equal to what we have inside our brackets. So it's getting to be a little bit of a mess. I'm going to have to redraw it down here. So let's do it. Let's redraw it down here. So we have 168 T is equal to pressure drop over the filter cake, which we said was the viscosity, the specific resistance of the cake, the dry cake mass per unit volume of the cake, the area squared, dV dt, okay, and then V. Okay, where V is the volume of filtrate. And that's what we mean by hint just here, comparing the cake filtration equation and the empirical equation for pressure rise. That's what we've done. We've compared them and come up with this equation here. So if I take T over here, then that comes back to what I said at the start, where dV dt equals V over T. So we can simplify that. We still need our viscosity, specific resistance, dry cake mass per unit volume of filtrate of the cake, area squared. We still need all those, but we can go either way here. I'm just going to go V over T, and it comes V over T squared. Okay, this is what we want. So this is basically what we're rearranging everything for, and clearly what we need to do then, let's not forget to do the square root this time. So we have V over T is equal to 168 divided by, it's going to look like a hell of a mess when I write it out. I could actually, I think I'd rather leave it as divide by this lot. Could turn it round and multiply, but I'll need to kick up the spreadsheet, and we have the spreadsheet populated already. This is the top row where we have the viscosity, that's 10 to the minus 3. Then we have the specific resistance, which is 6.7 with all those zeros after it. And then the dry cake mass per unit volume of filtrate at 116. So that's been calculated on the top line there. That's just the area squared, and then that is the the top line divided by the area squared. So that leaves us with the calculation of 168 divided by what we have just calculated, and then we need the square root. So that's equal to SQRT, what we've just calculated here, which is 4.6 times 10 to the minus 6. So that is 4.6 times 10 to the minus 6 meters cubed per second, and that is the square root, because we had the square just here. So the answer is 4.6 times 10 to the minus 6 meters cubed per second. Okay, the next bit then is the time taken to achieve the filtration. Just move it over a bit so you can see better. 4.6 times 10 to the minus 6 meters cubed per second. If we convert that into litres per second, that's 4.6 times 10 to the minus 3 litres per second. Okay, so the time taken to filter 4.6 litres, which is the total volume of filtrate in the first question, or in the previous question rather, would be 1000 seconds, because we're 4.6 times 10 to the minus 3 seconds. So the time taken to filter the total amount of filtrate, which is 4.6 litres, would be 1000 seconds. We're only filtering 2.3 litres. The question only asks us to filter half the filtrate, so in other words, it's just 500 seconds that it would be the time taken to filter the 2.3 litres. It's at this stage that the filtration changes from being constant rate to constant pressure. You'll see that in the next question. So this question is the sort of forerunner for the next question, which follows pretty much the sort of thing I was talking about with the filter press, where it's constant rate then followed by constant pressure. That's what we'll have here. So that leaves us with the medium resistance to calculate. Okay, for the filter medium resistance, just move that into a better position. We have the equation that mu Rm over A dV dt equals 6670 pascals. So if we want to rearrange that, we end up with Rm is equal to 6670 times by divided by dV dt rather. So that's over, let's call that Q. Then we have A and the viscosity underneath here, the area, and then the viscosity underneath here, which I think I've already populated. Nope, I haven't. That's okay. So for the medium resistance, we have equals 6670 times by 0.0314 divided by, we better put this all in the brackets, Q is 4.6 times 10 to the minus 6.06, and then we've got the viscosity 0.001. Okay, that gives us a value of 4.5, and the only 4.5 in here is this, and in fact it is 4.5 times 10 to the 10. All these are reasonable RM values, resistance to the filter medium values, reasonable ones, but in our case here it's 4.5 times 10 to the 10, and that's meters to the minus 1 are the units there. Okay, so this is a constant rate filtration, but it leads on to the next question where we have constant pressure. So we've filtered 2.3 litres under the conditions of constant rate. Okay, we're about to filter the rest of the 2.3 litres under conditions of constant pressure. Only here we're now going to be using all the filter cake that we've formed as the effective filter medium in the next question.